Stanford University.
Our guest. Thank you. Welcome, everybody. Glad that you could show up. I'm always happy to see lots of faces in the audience. Feel free to interrupt me anytime for questions. As Stephen was just saying, that very, very recently I was just at Palo Alto Research Center, where I led a group of about 7 PhD researchers in an area called augmented social cognition. And a lot of the work that I'll be presenting here will be the work that I actually did there with them, and so they should get a lot of the credit. But starting on Monday, I started at Google Research. What I wanted to spend some time telling you about is actually a tale of 2 stories around some of the effort that had happened at Park around building social recommenders. I wanted to start this by giving you a little story that some of you may have heard. How many of you know about Randy Pausch? Okay, hopefully if you're in the HCI seminar, you have heard about Randy Pausch. And if you have heard the story, you would also know that Randy Pausch passed away some time ago. He was a professor at CMU who was diagnosed with pancreatic cancer around 4 years ago now, if I didn't remember that correctly. The interesting thing is that at the same time, a person that was very close to me was also diagnosed with pancreatic cancer. And so during that entire period, I was using a lot of what I know best as a research scientist, which is all the tools that are available to you, including search engines like Google, and social bookmarking systems like Delicious. And what I was doing was doing the research on what happens to somebody when they have pancreatic cancer. And if you bother to look this up at all, the diagnosis for pancreatic cancer patients are pretty grim. 95% of the people do not make it past the 5-year mark. So it's a very deadly form of cancer. And after I started doing this, the bookmarking and researching and putting all this material online, including editing Wikipedia articles, etc., just a couple of months later, I actually got an email from somebody, and this is a person I had not known at all. And while I've been telling you this story, maybe you've already read the email, but he basically said, I've noticed that you've been bookmarking a lot of stuff on pancreatic cancer, and I just want to reach out to you to see whether either you have been diagnosed with pancreatic cancer or if there's anything at all that I can help you with. And I now actually follow Brad on Twitter. And we actually have conversations regularly, and we sent support emails. I've never met this person yet, even after 4 years. My father-in-law, who was diagnosed with pancreatic cancer, is still alive, thanks to a lot of information I learned on the net. So the interesting thing about this story is that the conventional wisdom at the time in 2006, 2007, not long after Joshua Schachter developed the Delicious bookmarking service, is that everyone says the reason why it works is because people bookmark things for themselves, and the social aspect of this system is really just an accident. Well, is it? My experience certainly points to the possibility of connecting to other people through these kinds of social systems. And is this experience isolated? Not too long ago, I had my birthday. My birthday is on November 13th. And the conventional wisdom, of course, again, is that most people don't really care about your birthday online. And even if they do, maybe they care, just a few of your closest friends might care. Well, someone noticed on Facebook that it's my birthday, and this is the traffic on my wall after about 5 or 6 days continuously after my birthday. Now, of course, I'm someone who does social computing, and so I took actually to spend time to actually respond to every single one of these messages. And I started thinking, you know what, as a computer scientist, wouldn't it be great if I just built a little robot that would reciprocate anybody who sends me a happy birthday message, so that I would remember on the day of their birthday to send them a message. And then I realized, wait a minute, there's something that you really take away from the social experience when you built this thing to be automatic. So it's not about automation. And so there's something interesting going on here with the fact that people apparently do care about your birthday. So another common saying now on Web 2.0 world is that people wouldn't really care about what you had for lunch, right? So who cares if you had burgers, or I just had pizza with lots of HCI folks. So maybe I would have tweeted, had interesting pizza lunch with HCI folks. And the conventional wisdom would be that people wouldn't care. Well, a week before my birthday, I don't do this very often, but I happened to check in on Facebook at a restaurant that I was at, Followi. It's a Vietnamese restaurant not too far from the Stanford campus here on El Camino in Los Altos. And David Ayman Sharma, who's a researcher at Yahoo Research, actually replied and said, good pho? And I said, yeah, actually, I think it's probably the best within the 50-mile radius. And a person that doesn't even know David, but is a friend of mine, replied and said, I like number 12 large there. Again, the sociality here is surprising. So people apparently do care about what you have for lunch. But maybe this is just an isolated incident. I mean, maybe it just so happened that there aren't so many Vietnamese restaurants around, and so if anyone talks about a Vietnamese restaurant or checks into one, then people are interested. Well, a week later, I was at a ramen restaurant in San Jose called, actually not in San Jose, in San Mateo. And this time, not only was there messages, but there was actually a discussion. There were 4 comments of going back and forth, whether there's MSG in the soup or not, and etc. So apparently people do care about what you have for lunch. So all this is surprising in the sense that clearly different people want to hear about different things at different times under different contexts. And the problem is that in the offline world, we have all this context in which to route messages. Right, so one set of people here might be your closest friends and family, so you wouldn't mind sharing the fact that you might have just broken up with your girlfriend or your boyfriend. But your professional colleague that you met at a Chi conference 2 years ago may not care about the fact that you've been crying your eyes out, right? So in the offline world, the way that messages transmit sort of somewhat self-corrects for some of these problems. But in the online world, at least if you think about Facebook's model of how the world works, is that messages are broadcast to essentially everyone in your social circle, or that one friend is the same as another friend. Of course, they have these things called EdgeRank algorithm, which you can Google and read up about, where they try to prioritize messages, etc. And that's their solution to the problem. But the fundamental problem from a user experience perspective is this one, which is that the online world, the way that you form your friendship on the online systems don't match up with how you actually behave in the offline world, or at least how the structure of the offline relationships are put together. So the way in which we find information in the real world is dependent upon a number of different things. It depends on the strength of your relationship to other people. So in social network theory, I noticed that John Kleinberg and other folks have been speaking here at Stanford, or will be speaking here, who obviously can tell you about all the mathematical theories behind some of these kinds of things, where you can compute and model all these social relationships. But at a conceptual level, there are these relationships that are strong ties, and there are these relationships that are weak ties, and then there are these relationships that are temporary ties. In fact, some of these concepts I actually learned from Scott many years ago at a HCIC seminar, where you talked about proxemic theory from Edward Hall, I believe. And that, that was before I was doing social computing research. So I have you to thank for thinking about a lot of these kinds of problems. But the kinds of information that you discover through these different relationships are different depending on the kind of relationship that you have. And so the system I'm about to tell you is sort of in two parts. There's two systems. One part is about social discovery and learning via delicious, where these kinds of relationships are really sort of very far out, more than arm's length relationships that you might have with the rest of the world, the rest of the people who use delicious in the entire world. And then the second part of the talk will be about how to use these kinds of relationships that are closer to you for discovery. So the first part of this talk will be about how do we use social bookmarking data for discovery. Social search is a term that has been thrown around a lot. There's really sort of one possible area that I think where social search might have some win over other kinds of search. We know from web search engine literature that for the most part people talk about three different kinds of important searches that occur on search engines. The first two that are fairly easy to solve are what's called either navigational or transactional searches. So transactional would be the kinds of thing where you're actually trying to do a transaction. So for example, you're trying to buy something. So you go to eBay and you look for a pair of, say, snowboard boots, right? And your objective is to actually make a transaction. Or the transaction could also just be looking up your bank account. So that your first step might be look up where Wells Fargo is. So you know what you want to do. You have a very, very specific transactional goal in mind, and you want to go and do that. 13% of the searches we know from search log analysis is of transactional nature. Another 28% of searches is navigational. So you know what you want and roughly where it is, but you're not seeking to do a transaction. You want to navigate there, digest the information. So for example, let's say the earlier thing that I was mentioning, navigational might be you want to find out what store has the item that you want. So let's say, for example, you just injure your foot and you like to get some ice packs, right? And you know that you probably should look at CVS Pharmacy, so you go to the CVS Pharmacy website and you look up the closest store, and then you drive there, right? You're not going to order ice pack or online, because by the time it gets to you, it's not going to be very useful. The third kind of search is informational search, and it's 59% of all the searches. You roughly know what you want, but you don't know how to find it. So the kind of search that this might be would be, for example, a loved one just been diagnosed with pancreatic cancer. You got to learn about what are the treatment options, what are the survivability, if they have to go through chemotherapy, what would be the side effects, who are the best doctors, who are the best hospitals to go to, do I need a second opinion? You have a lot of, it's the kind of informational search that I'm thinking of is the moment that you find out a piece of information, you have more questions. It's like opening a can of worms that you just keep going and you can't, sort of quite finish with it. Now that I found out that CVS is open from 8 to 6, I'm done, right? I just go there. So that's nicely and contained. And these kinds of searches are typically more difficult for existing search engines, and we think that social attention data might be a very good way of solving some of these problems. So, yeah?
How do you arrive to those percentage numbers?
You can do this kind of analysis through either weblog analysis, or you can do surveys. We were talking about Dan Russell up in lunch. Dan Russell at Google has been publishing a lot of great work in this particular space, along with her colleague Ann Alla. So if you're interested in figuring out all the different strategies in which you can arrive at these kinds of numbers, I would encourage you to read that literature.
These numbers are valid universally?
Yeah, I mean, they're valid in the sense that I'm giving you some numbers that are rough proportions to give you a sense of sort of the amount roughly in each category. But of course, it depends on the study and the kinds of weblog, the kinds of search engine that you're talking about.
And the boundaries between these categories, the forests and
all those kinds of hand-wavy caveats. So our idea was that maybe we could use social attention data to do some form of social search that would be better than existing search engines. So in 2008, along with the intern, we started thinking about the social tagging problem in a particular way that I thought was kind of interesting, which is that if you think about how people use tagging systems, they're essentially looking at these documents which are about certain topics, and as they read these documents, they form ideas about these documents, what they're about, and they have some sort of knowledge structure, if you will, in their heads. And what they do is essentially this encoding step. So they say, oh, this document is about pancreatic cancer. So they type in pancreatic and cancer, and they say, I want to remember this web page by those two keywords. Those are what are called tags. And then the problem is that a couple months later, I go back to the system, and I want to look up things about pancreatic cancer, and I have this decoding step. What was the word I used? Okay, so did I use pancreas or pancreatic? Did I use the word cancer or cancers? And did I use the word disease, health? What was the category that I used? And what's worse is, of course, we talk about folksonomies where it's social, meaning that I don't know whether you used the word pancreatic and if she used the word pancreas, or maybe some other word that maybe even PC, because you decided to abbreviate it. So there's essentially this noise that is part of the process. And so if you think about social tagging in this framework, you realize that it actually fits very well in Klaus-Shannon's information theory, that there's an encoding step and a decoding step. And so you could use Klaus-Shannon's information theory to actually analyze the amount of information that is actually present in social tagging systems. And so we had a paper that went through this entire analysis. So for example, you can analyze the amount of vocabulary saturation, which is here on the left-hand side here, where you have the entropy of tag changing over time. So for those of you who haven't taken information theory, entropy is the measure of think of it as for a measure of chaos or amount of uncertainty. So in other words, think about it as gambling. Okay, so imagine that you're Delicious and you're waiting for tags to come in through your service. And you're trying to make bets about what is the next word, right? Is the next word pancreatic, or is the next word pancreas, or is the next word Java, or is the next word whatever? And how high this graph on the left-hand side here specifies how easy it is for you to make that guess. The higher it is, the harder it is for you to make that guess. Okay? Yes?
Question of scoping, going back to so tag is what people repeat.
Mm-hmm.
So the grammatical category is generally noun, sort of sometimes barely even noun phrase, probably noun. So the assumptions are with respect to that, rather than say some description of a process.
No, not necessarily. People actually do use verbs and so treatment, for example, might be labeled as treating. So they might label something as treating pancreatic cancer rather than treatment pancreatic cancer. And that all of those kinds of language morphologies exist within Delicious. In fact, the variety of it is what makes it very difficult for categorization. Yeah.
Phrases, grammatical phrases.
Oh yeah, absolutely. So I'm sure there's people who tag that, treatment dash cancer, for example. I'm sure that's probably a keyword.
As atoms or always keep going side?
Sometimes with underscores in between, sometimes with a dash, sometimes with capital cases, all kinds of variations. And so using this sort of methodology, we can actually analyze how much information is being stored inside of a social tagging system. And the moment that you start to having this kind of entropy view or information theoretic view of social tagging spaces, you realize that you could actually analyze things like, for example, mutual information. So this is about, like, if I tell you the distribution of tags, if I told you sort of the interest over all the different keywords that exist within, within Delicious, what can you tell me about the distribution of documents, right? You should be able to make some prediction. If people are very interested in Java, then a lot of documents will be about Java. If a lot of people are interested in pancreatic cancer, then there will be a lot of documents about pancreatic cancer. So if I told you about what the keywords are, you should be able to make a decision about what documents exist in the system. And your ability to make that prediction is conditional entropy. And mutual information is the measure of your ability to make this guess on both ways. So if I told you about the distribution of documents, now you should be able to make a prediction about the kinds of tags that people are using. Your ability to make that prediction and vice versa is called mutual information. And what this is showing in this graph is that your ability to make that prediction actually has been going down over time. So what lower is worse in this graph. So what that means is that as a navigational system, social tagging systems was actually getting worse and worse in encoding the information that's inside of it. And the reason for this is obvious, right? Now that you've thought about this for a little bit. In the beginning, when there's, say, 100,000 documents in Delicious, if you type in the word Java, maybe it will return, say, 10 documents or 100. But now you go to Delicious and you type in the word Java, you probably get close to 1 million, maybe much more, right? So you have to specify a second keyword to say, I'm actually interested in Java API or Java strings. So the way in which you combat this decrease in mutual information is actually by raising the number of keywords that you specify to the system. And this is exactly the same parallel process that happens in search engines. We know from search engine log, again, analytics, that as the web has gotten bigger, the way that people are combating the increase in information by specifying more search keywords. It's been going from 2.4 to 2.8, 3.4, and I think more recently is something like close to 4. We should ask Dan, but it's probably close to 4 search query words per search at this point.
The other way to solve this is to use something other than keywords to help guess what's likely to be relevant document.
Yes, so perhaps a personalized search system, for example, might help. And there's other ways of dealing with this problem, absolutely. But one of the ways in which that this is happening is this. And the right-hand side shows that, you know, indeed that this has been happening in the social tagging system.
So I'm also curious because you said that your corpus is becoming more diverse, which is why you're doing more tagging. So if you plot this versus, say, the entropy within your corpus, what is that? Mutual information of document and tag versus the entropy within the corpus, is it more or less a straight line?
I see what you're saying. You want to normalize it in some way, right? That's the whole point of mutual information is essentially should be able to take care of that normalization already for you. But I probably have to think about that question a little bit more deeply using equations than I can have time right now. So let's talk offline on that. And so once we have this realization that you can model this system using this kind of approach, we realized that you could actually compute all these conditional probabilities using a distributed computation system. So we built a cluster of machines at Park, 60 machines, and we put Hadoop on it, and we did the whole, PageRank MapReduce kind of computation on top of 150 million bookmarks, and we basically are able to. I don't have time to go over the time for the equations and all that, but what you end up with in the end is this sort of semantic similarity graph that tells you something like, for example, that tips is very related to tutorials, and this is very similar to word co-location analysis in traditional information retrieval. But beyond that, you also actually get the documents in as part of the mix. So think of this as a version. If you've taken IR classes, this is a little bit like LDA. And What's interesting about this is also, of course, because we're using organic information from people, we also find out a lot of somewhat surprising similarities that you wouldn't normally think of. And in fact, Google uses some of these signals for their spelling correction. It turns out that tutorials with an R is a very common misspelling of tutorials. The reason is because if you look down on your keyboard, T and R is right next to each other. And so when you use a tagging system and you specify tutorials rather than tutorials, it actually does quite well. So in fact, let me give you a quick demo of this. Mr. Tag. So actually, so if you type in tutorials, tutorial without an S, you see that it says, well, you might be interested in tutorial. It looks like it's also related to the keyword how to, reference, code, script, etc. So this is our prototype system that we call Mr. Taggy. And let's say, for example, you type in a query that is a little bit, I like this example, JFK, because when I did this search, I was traveling to New York City. So when I type in JFK, I was thinking of JFK, the airport. And of course, when you type in JFK, the system says, actually, you're interested in the person probably. So that may suggest history, conspiracy, politics, assassination. And I said, no, 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 no. I'm not interested in assassination. I'm not interested in conspiracies. I'm interested in airport. That's good. And you can see now it says, if you're interested in JFK and airport, but not interested in assassination and conspiracies, you might be interested in US helicopters that are scheduled between Manhattan and New York airport. I looked at this and I said, that's too expensive for me. But AirTram, the subway, that sounds closer. But if you look through the search result here, everything here, oh, there's sharing a taxi as well. Everything here is about traveling between the airport and Manhattan or New York City in some way. If I go back to the beginning here, you'll see that all the results here, except this one, seems to be about, here's another airport one. So about 2 out of, oh, this one, no, that's about the assassination as well. So 2 out of 10 in the top results were originally about travel. So very quickly, I can move in this sort of tag concept spaces using this concept. So that's the idea behind Mr. Taggy. And what we're doing is essentially using all these social signals that are out there that people have tagged. This keyword often is tagged with this other one, and it's often used with this document. That document is about these keywords, right? And if you do all that analysis, now you know the concept spaces and you know the document spaces. And you can move between either one. So for example, if I type in fitness, and normally when you say the word fitness, people think of exercise. But of course, fitness is also about diet, right? But if you type in fitness, the search engine is going to try and use the first sense of the word as much as possible, right? And using traditional sort of IR technology, you say, okay, you must be interested in bodybuilding and exercise. Oh, diets, yeah, that's good. I like diet. So let me say yes to diet. And these are all links that are about fitness and diet, right? So very quickly, through one link, you can move to an entirely different concept space. That's the idea behind this system.
Can you talk a little bit about your choice of the interface?
Sure.
I've seen these in the past, stuff like this where they show the cloud and all the connections, and that just seems like the wrong way to go about it. Too much going on. This is a really smooth way of navigating that cloud, but without showing everything.
Obviously, I work with Stu and Jeff on a lot of these sort of information visualization ideas about how do you represent concept spaces. And we're constantly still struggling with the UI design decisions about how to deal with these problems. Is it better to sort of represent concept using a linear sort of, I think this is the top ranked, most interesting, relevant thing to you, versus a 2D space where you have things maybe laid out in force-directed ways or other representations. A lot of the research so far in the web interface side seems to have shown that we underestimate the amount of information that people gather from keywords. Being able to read, if I type in fitness, my sort of simplified version of this, if I type in fitness and if it says, I know about fitness, and it's about these 5 different concepts, and maybe it's just 1, 2, 3, 4, 5, which one of these are you interested? Select or multi-select the ones that you're interested in. Maybe you are indeed interested in both the exercise and the diet because you want a comprehensive plan for both diet and exercise at the same time. Maybe other times you're only interested in the exercise aspect of it. And so when we designed this interface, we started with thinking about how would the user approach this problem, right? They would approach it in the sense of, I want to specify to the system which one of these things I mean. And that's why we came up with this system rather than sort of this visualization way of representing it. OK, let me get back to the slides for a second here.
Do you know if there's been a major search engine that tried this thumbs up, thumbs down approach? Because it seems really compelling. I think for simple Google searches, what I want is often on the first page. But there are more complicated things where it would be nice to be able to do exactly what you've shown with Mr. Kagi, which is this, not that. Mm-hmm. Why isn't that more widely available?
I think some of the interfaces that people have started, the auto-completion, for example, is sort of a version of this, right? You type in FA into Google's search engine and it will auto-complete to Facebook. And it's sort of making this sort of prediction about where you might want to end up at. But it also gives you other suggestions. And in fact, I think Fernanda, not too long ago, here had shown some interesting visualizations of weird completions that people have. But that's one way in which you can enter into a dialogue with the search engine where it's sort of making some suggestion to you. I think we're sort of showing a version that may be a little bit more advanced than that. But I think we are moving toward that direction, the world that is.
I think Bing has or had something like this for image search. Take an image. I like this one.
Yeah, Google also ran that. You could rank their search results for a while, but then they got rid of it. Unclear why.
OK, so that was the video, just in case the demo didn't work. And the way in which we built this system was actually fairly complex. All right, so we had a crawling system that actually went and crawled all the bookmarks, and then we put them into a big database. That is then thrown into a MapReduce, where we crunch over all this computation, the probabilistic manipulation, and then the patterns from that computation, the result of the PageRank computation, if you will, is then stored in the Lucene database, and that is then transferred over to a web server, and then we have a front end that deals with all the interaction and all that. And this system took us probably about 2 years to build from end to end. And one thing to originally, I'm glad that there's a lot of good questions, but I'm going to skip over much of the evaluation of this system. But I want to say a word about that evaluation, which is that users who lack sufficient knowledge in a particular problem space. I started this section with talking about exploratory search. We call these kinds of search spaces ill-structured in information science. Okay, ill-structured for you, meaning that if you are thinking about pancreatic cancer and you have no clue what cancer is about, right? The word, for example, chemotherapy might be in your lexicon, but Tarceva would not. Tarceva is a particular drug that is often used in various different kinds of GI cancer. And again, GI is another special word, GI meaning gastrointestinal. So these spaces is ill-structured for different people. And in some cases, you might be novice in one space, for example, pancreatic cancer, but you might be an expert in another, like, for example, HCI. So if I asked Wendy to give me a taxonomy of HCI research, she'll probably do a very good job of giving me lots of keywords, right? So a problem may be ill-structured for you in a particular area, but you might be an expert in another. And so what's interesting is that we ran an experiment using Mr. Taggy without sort of this ontological, sort of this structural help on the side, where you just use the standard sort of Google keyword, modify the keyword exploratory interface, versus a true exploratory interface, the one that I just showed you. And we had a complex design where we had different kinds of tasks and procedures and lots of results, which I don't have time to go after. And if you're interested, I'd be happy to tell you about it. But here's the summary of what the experiment showed. The exploratory interface users actually perform more queries. So normally, if you're evaluating a navigational or transactional query, you would say, that's bad. People are performing more query because they can't find what they're looking for, and they keep looking for it until they do, right? So that's bad. They took more time. That's also bad. We got to get people to what they need as quickly as possible. However, they wrote better summaries. So we gave people these tasks, and then afterwards, we asked them to write, kind of like in high school, read this article and then give me a one-paragraph summary of what you learned in the last 12 minutes, kind of thing. We asked them to write some summaries, and in 2 out of the 3 domains we gave them, they were able to write better summaries according to judges, essentially. And they generated more relevant keywords. In other words, if I asked you to go and look for pancreatic cancer information, and then afterwards I asked you, please now write down a list of relevant keywords to pancreatic cancer, you would be more able to generate better relevant keywords in that task. Again, in 2 out of the 3 domains. And by a measure of NASA cognitive load measures, you had a higher cognitive load. Again, in a navigational query where I need to get to that ice pack right now, right? You don't want high cognitive load, right? Should I be typing opening hours, or should I be hours without the S, or, you know, I mean, you don't want to have to go through that computation. So all these results seems to suggest that in exploratory interfaces like this, you actually do want maybe more queries and taking more time and deeper engagement and better learning. I mean, better learning is really the metric that we were trying to get at. So there's some interesting connection to educational psychology here. Yeah.
I'm curious what the domain was that seemed to give, it seemed for the exploratory user interface.
Yeah, we didn't have a good answer for that, but I think they were the same. It may have been due to task design. I have to look into the detail of that. But the domains were future architecture, global warming, and web mashup. You can see that they're very, very different areas. So our hypothesis at the moment has to do with prior knowledge. And we had in the procedure, we actually tried to take the prior knowledge out of the learning task. So we had a normalization thing. So more study is needed. Yeah. Okay. So that's the end of the first part. The second part I wanted to tell you about is social news recommendations. So you remember I started this talk by telling you about there are these sort of strong social ties and there's these sort of weak or temporary social ties that you can take advantage of. And these are all social signals. And in Delicious, the version of the system that I just told you about, we're trying to take advantage of these sort of global social signal that everyone leaves behind, right? At least if you participate in Delicious. By the way, you already do participate in some of this that you may not be aware of. Every time you do a search on most major search engines, you leave behind a trail. It won't be tied to your IP or your identity unless you opt into it. But you do leave behind a trail, and search engines do use that as a way to optimize their search engine. That's another example of you being in a part of a social search engine that you're not aware of. But that is social signal that people are taking advantage of. In this second part, I want to talk about how you can use close social ties to enhance information signals. We all know that these kinds of interfaces like Facebook, Twitter, Buzz, have all become very, very popular in the last couple of years. And the problem is this, right? Where should I focus my attention on? I don't know anybody who reads all their Facebook messages. At least if you're on Twitter and you subscribe to a decent number of users, it's also very, very difficult for you to get through them. My typical mode of operating within these kinds of information streams is basically I dip my toe into these streams every once in a while. So I might be going to lunch, and I'm standing in the lunch line waiting to pay, and I have literally 50 seconds, no longer, right? And then I pull out my phone, and I say, OK, what has my HCI friends been talking about lately? What's the most interesting thing, right? So I might call that the filtering problem. So I have thousands of items that has been happening over the last 24 hours. Maybe the last time I checked in was yesterday when I was in the lunch line, right? So I only have time to maybe read 1, maybe 2, maybe 10 of them. So which one should I read? Another problem that I have is that it's what I would call the discovery problem. There are millions of URL that people are talking about. And so the problem is a little bit different from the filtering problem in the sense that I'm presenting to you right now as an expert. I'm saying that I'm an expert, basically, in social computing. But if you come up to me and you say, by the way, have you heard about blah, 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 blah? And I say, oh, really? I haven't heard of that, right? That's a problem if everyone else is talking about it. So for example, the fact that I woke up this morning and I noticed that the Egyptian president decided to step down. Huge news, right? I mean, and it's all over Twitter, and if I don't know about it coming into here this morning, and you ask the question about, what's going on Twitter with the Egyptian uprising, I would not be seen as a social media expert, would I? So I call that the discovery problem because there are millions of things that are happening out in the world. Which one of those should I be knowing about that may not have been in my stream? That's the point. That the discovery part is that I should know about it, but it's not in my stream, right? So we know information and news get discovered through these sort of weak and strong ties. And there's a lot of interesting academic research that seems to suggest that a lot of interesting information typically come to you through weak ties rather than strong ties. And the reason for that is because your strong ties are probably very similar to you and are reading very, very similar information sources. And therefore, what they discover is probably very similar to what you discover. So they might be able to enhance your signal in the sense that they might help you do deeper analysis, but they may not be very good at discovery of new information. On the other hand, weak ties typically are sort of working in related areas. So for example, Yuri Leskovich, who works in social networking theory. It's not my core area. It's an area that's very important to my research, but it's important enough that I should be paying attention to it. He would be a very, very good weak tie for me because he would constantly be feeding me good information. Scott is another really good one. That's why I learned about proxemic theory, right? Several years ago. So the interesting thing is about that these news travel in these spaces based upon your relationship to them, the content that's being communicated, the urgency of that information. So the Egyptian news, for example, if I learn about it a week from now, it's not very interesting, is it? So the fact that it happened this morning, very, very important. And it's best to communicate that within the half an hour or whatever time frame that it is in. And the level of privacy is also very important. Paul Adam, whom I sourced a lot of these pictures from, gives this example of a teacher in New York who decides to go out on a town to celebrate some birthday and has some pictures of her drinking in a gay bar, and she's a teacher in an elementary school and got in trouble for posting these messages on Facebook, not realizing that some of her students are also her Facebook friends. So the level of privacy that's required also matters in whether the information should travel. So the way in which information travels is very complex. And so if we wanted to build a recommender to help with this problem, can we solve some of these contextual problems of making predictions about things that you should know about? So we built this system called 0088, which was using Twitter as the underlying messaging platform. And the interface basically looks like this. And it works on your iPhone too. So you basically log in and it says, here are the top 10 news items from your information stream that you may want to be paying attention to. And so this list is completely personalized just to you using the information stream that we know about from Twitter. And how is this system built? The idea is basically we want to model your interests using both content and the social network. So on the one hand, from Twitter, by crawling your account, if you give us permission to, we can find out the kinds of content that you have been paying attention to. So for example, James Landay tweeted at some point in time that a phone that helps with English education, health, and energy conservation, yes, see Professor Kenny's work at UC Berkeley, right? So the fact that this item shows up in my stream tells the system that I'm interested in Professor Kenny's work, that I'm interested in James Landay's work, I'm interested in potentially in phones, in HCI, relating to education, to health and energy, right? So you probably want to do some sort of topic analysis of the content that's there. On the other hand, the other part of the signal here is who I'm following, right? So all these people I have hand-picked, hand-curated to say, these are the interesting people that I'm interested in hearing about in my information stream. I may not have time for them all, but I'm interested in hearing from them, right? So I might not read every single message from Wendy, but I'm certainly very interested in what she has to say, right? So in designing this recommender, and then we just basically sat down and said, okay, what are some very basic features we want in the system? We said, on the one hand, we have a problem of selecting candidate URLs or news items that we want to show to you. What URL should we consider to be candidates? That's one problem. Another problem is ranking. Okay, so ranking might be ranking using topical relevance or ranking using a local social neighborhood. And I'll go through the detail of this in the following slides. So as far as the discovery problem, I mentioned that there was a filtering and the discovery problem. From the discovery problem, this is where it's important, where you select the candidate URLs. You can either choose to select URLs that only are being discussed within your social network, right? So the computer science department here, for example. So if we can somehow magically have this black box that let's say, for example, puts it in front of the internet that comes into this building and capture every single URL that comes through this building, and then we count out the frequency of that, right? Now we know sort of this local community and the URLs that people are interested in inside of it. Jeff?
Clarification question. Are you assuming that Twitter followers or followees are strong ties? No. It doesn't seem to me that that's true.
No, that's definitely not true. And I'll get to that in a second. Basically, what we do is we actually get at that social network, and then we do essentially a network constraint modeling to find out who is a strong tie and who isn't. Yeah.
So you're taking URL as a perfect proxy for topic?
At the current moment, as a proxy for news items, not for topic. Okay. And I'll get to the topic part of it in just a second as well.
So small document, but there's something else out there.
Well, they could be small document. They could even be videos. So these are URL items, which is just sort of items that you can go to by clicking on a link. Not necessarily. It could be a YouTube. It could be a lecture. It could be a news item like like a CNN's headline news item. It could be I went to Followi yesterday, a Facebook message. So two options. One is selecting from your local community. The other is URLs that are globally popular. So lots of people are talking about Britney Spears, or lots of people are talking about, what was it? William was selected as the innovation person for some company some time ago, right? Sun. Right. That's an example of something that I wouldn't care about, but is globally popular. And then on the ranking side, we can rank both by topical relevance, or we can rank by the sort of social voting, how many people in your social network are paying attention to it. On the topic side, we ran into a problem. So a lot of people actually listen to the streams. For example, they'll log on to Facebook, but they won't actually post anything. And so as a result, we only have things that are coming into their stream, but not what they post. So we don't have explicit signals about what they actually talk about. We only have what they listen to. So as a result, we can model people's topical interests in a wide variety of ways, and we just pick two ways. One is either based upon what you actually said on Facebook or Twitter or whatever. The other would be to actually follow what your friends say on the network as a proxy of what you might say. This was kind of an interesting choice. So we call that the Followi topic model. And then another possibility is actually to ignore topic completely and simply use a social filter. And the way that we did topical relevance, at least in the first version, was very simple. We basically did the traditional IR technique of using TF-IDF and calculating what are important words, so the kinds of things that you would expect. Later on, we used a more complex model, but this is the way that we did it initially. As far as ranking using local social network, we use the concept that we call voting by posting. So the idea is that the more people in my local social network posted this URL or talked about this URL, the higher it would be ranked. And another part of this is that the more people in my social network trust you, the more your vote matters. So this sort of partially answers what Jeff was just asking about. So let me show you by using a picture here. So if you're this red node here, clearly you're more interesting because you're well connected. If you say something, these other folks would pay attention, or at least would show up in their stream. Whereas this person were to broadcast a message would not be nearly as important. And so by using these sort of social, I realize I'm hand wavy, but you can go read up on Yuri Leskovich's work and understand how to do this kinds of computations. But basically, you can calculate these kind of social importance score and model people in these networks. One thing we threw in here that was kind of interesting, and is still an area of further research, is one day I had this hypothesis, is that if you hardly ever post on Facebook and all of a sudden you post something, chances are your friends want to hear about that. So people who rarely speak up and all of a sudden they speak up, it's probably an interesting measure of importance. And the flip side is, of course, also true. You probably all have these friends, Facebook friends or Twitter friends, who post constantly. Oh my God. And you know what? Sometimes you just want to hit the mute button. And so we have a little algorithm that tries to take care of these kind of normalization. So in very quick summary, basically these are the various different ways you can build this recommender that we just very quickly thought of and thought about how to build it. And we said, oh my gosh, this is a lot of different choices. What do we do? Do we implement 1 or 2 or 3 and then just see which one works? We said, oh, heck with it. Let's just do the brute force approach. We implemented all 12 algorithms and then evaluated them. This is the architectural diagram that basically just summarizes what I said. The green part here is basically the selection problem, what URLs I'm going to consider. The red section here is talking about the topical model, how we build it. And then the social recommendation part, where I use the network as well as their tweet patterns to calculate essentially a social importance score. And then these two models are combined in order to rank the URLs as recommendations. And so we did essentially what we called a living laboratory field study. So we implemented all 12 algorithms, and then we recruited publicly on the Twitter network. Please come and use our system. The only limitation is that you have to have at least 20 friends. We hope you're at least social enough to have 20 friends. And that you have at least tweeted 50 tweets. And the reason for that is because we want to give each algorithm a fair chance, right? So if we have algorithm in the mix where, so you might ask, well, if most people don't tweet, then obviously this wouldn't be a valid experiment. But the point is that we wanted to evaluate it so that there's at least enough data for everybody for an algorithm to have a chance of succeeding. So over a 3-week period, we recruited 44 users who used our system and gave us ratings. And for each of
the participants tweet, why doesn't it work for lurkers?
It won't work, just not for all the algorithms. So for the case where we're ranking using the topical relevance, if you don't tweet, then we can't build a self-topic model of interest for you, in which case that's one path through the 12 combination that you can't do. So for each of the 12 algorithms, we generated 5 recommendations. So 12 times 5 is 60, and we have 44 participants, so 60 times 44 is 2,640 ratings. And we ask for a binary rating. Basically, you look at a URL, look at the discussion that follows it, and you give us a rating of, yes, I would be interested, or no, I would not be interested in this item. In other words, I'm either happy with the recommendation or I'm not happy with the recommendation. And so for the stat people who are in the room, the moment that you hear binary rating, you go, logistic model, and you would be right. So what we did was basically we collected these ratings, and we ran a logistic regression. And the research questions that we had would basically correspond to these design choices that we talked about. What kinds of candidate URLs should we choose? What kinds of topic relevance should we use to do the ranking? Does social ranking help? Does both social and topical ranking together work nicely together? Among all the 12 algorithms, which one is the best? So these are all just natural research questions that follow the research. Using the logistic regression, we did essentially a standard statistical analysis using SAS. And here's the summary of results. Your friends of friends indeed is better than globally popular. Exactly how much better? 25% better in terms of log odds. Okay, so I'm not going to go into the detail of how to explain probability ratios versus odds ratio, but that just let me be hand wavy and say it's about 25% better, okay, in terms of odds. What about topic? It turns out that self-topic is 79% better than not having any topical model, which is good. And that using your friends as a way to model what you might be interested in topic-wise is 31% better than not having any topic model. So that's good. So that means we can do some sort of IR tricks to sort of model what the kinds of things that you're interested in and use that as a prediction model of the kinds of messages you want to hear about. That's great. Here's the surprise. The social voting mechanism was 277% versus 100%, meaning that it's 177% better than not having the social model by itself. That is, this is not in combination with any other models. What about the question of combining models? It turns out that if you combine the topic model and the social model at the same time, we know already from the logistic regression that the social voting model was really, really good. So we'll put that first. Then now let's add the topic model on top of it, right? So can we improve on top of that? We can improve it further by 22% on top of that using the self-topic model. But using the Followi topic model, you only add 10%. And that makes sense, right? Because the social model ought to already have some social context inside of it. And so using the Followi model shouldn't improve it nearly as much. Yes, Wendy.
From the user's perspective, what a 10% increase in effectiveness.
I'm glad that you asked that question because that's the next slide. So here's the summary of results where these are all the 12 algorithms sorted in increasing accuracy score, if you will. Now, I haven't given you any sort of significance numbers here, but let's go through this slide in a little bit of a detail. First of all, if you just use popular URLs and just sort of imagine you have a system that just, like I said, count up the number of URLs that's flowing through some pipe, and then you just said, here's the top 10, right? How good would that do? About 33% or so. So that means 1 out of 3 you'll probably hit on something that people would be interested in. Oh yeah, it is interesting that the Packers won and the Steelers didn't. Yeah, I would be interested in knowing about that, right? Here's the interesting thing is that if you did the same thing, collected all the URLs from only your friends and your friends of friends, right, and randomly chose those URLs to show to people, you would get 33% accuracy as well. Okay, so well, that's kind of interesting. No other sort of ranking other than just randomly selection. Here's the interesting thing. Simply notice the pattern here. None, 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 none. Vote, 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 vote. Basically, the moment that you add social voting to it, and that's the 277% versus 100% I was talking about before, you get basically an order of magnitude improvement on the accuracy. So instead of 1 out of 3, now it's more like 2 out of 3 that you would be making an accurate prediction on. And the best algorithm here is around 72%, which is 7 out of 10, a little bit better than 2 out of 3, but not significantly better. So what's the moral of the story here? It sounds like social voting really, really works. And that's more than a surprise to us. Oh, that's just simply mapped to the strength of the prediction. Yeah, double encoding. Sorry, you might be an information visualizer. Why did you use a double encoding?
Do you see differences between false positives and false negatives? Like, for example, if I'm interested in topic X, and I tweet about topic X, it's plausible that I'd be interested in other posts about topic X. And so you discard everything else, and I like most of the stuff that you show me.
I'm so glad that you asked that question because it shows that you're really thinking critically about this problem. At the beginning of this section, I was talking about filtering versus discovery. And I think part of what you're asking about is about that issue. So that means skip over this part, which basically says you can imagine using this kind of approach to build other kinds of social recommender system. Hang on a second, I'll get to you. The interesting thing here is that even though what we've shown is that we can build these kinds of systems, that we can build social recommenders using both topical and social network, one of the things that we got back from our post-user survey from people was that, as academics, we like to focus on these accuracy numbers. Wow, we got 72% relevance, accuracy. That's great. But one of the subjects actually said, there's a tension between discovery and an affirming aspect of the recommender. I'm getting tweets about things I'm already interested in, which is great, but actually something that I really crave is the element of surprise or whimsy. I'm getting a lot of things I'm interested in, but that's not necessarily a good thing for me personally. So this person is saying that relevancy is not the same thing as good, meaning that for a recommender here, yes, I might tick off this and says, yes, I am interested. Yeah, this is relevant to me. This is relevant to me. I'm indeed interested in this other one as well. But you know what? This one not only is it relevant, but it's also the one that I'm surprised that I hadn't seen an idea like this before in the system. And that's more valuable than saying it's relevant.
There's this thing about more is better kind of thing versus there's this idea of something that's oversold, and you have that in terms of like these people who tweet too much, but there's also topics like that. So after a certain point, it stops. Like for example, nobody's tweeting about Tunisia at the moment.
Right.
They're tweeting about Egypt. And yet, I was talking to my son yesterday, and he was saying, well, so that was really cool what happened a month ago, and does anybody know what's happened since? I mean, is it doing well or not, or, and he Googled it, and had a very hard time finding anything. So what was, after a certain point, way over done, I knew way too much about it, and then a month later, now it's interesting again because, so there's a time thing and there's a whole lot of complexity in there.
So the one aspect of future work that we're interested in is this idea of globally popular, it's actually more complex than that. It's got a time element to it that we like to add back into the recommender engine, where it's the globally popular is actually time sensitive in some way. So yeah, you're right, exactly. I can't say much more. Okay, so I think I have okay, I actually planned on only one, so that's good. So a quick recap, right? So I started out giving this talk about thinking about what is it that is the kind of social information people are interested in, right? So what social news and information that people seem to care about is actually quite surprising. Because the different kinds of contexts that exist in real life makes different kinds of information important or interesting at different times. And the social context is actually a very good way of enhancing a lot of this information signal. In part one, what I talked about was using these sort of social cues that are really sort of from the entire world to build better sort of search engines, exploratory search engines. And it seems like we could do something about that problem by using this sort of global social attention data. In part two, what I talked about was actually not only in addition to the global social signal, we could also use local social signals to enhance your particular personalized news stream, your environment, your information environment. And not only that, we can actually combine that local social signal with traditional IR approaches of topical modeling of the kinds of things that you're interested in. They work in concert together, at least to improve relevancy. Now there's a whole discussion that we're just about to get into, and that's the purpose of the seminar, is to get further discussion. Like, what does it mean to have not just relevancy, but also on discovery, right? And I've been sitting up here to talk about all this work, but actually this is a whole team worth of work that's been happening over the last couple of years at Park. I'm actually suitably in the background here, and these are all the other people on my team. But however, if you do have any questions, that's the way that you can get a hold of me. You can tweet me or send me an email. And so I thank you very much for your attention. So I forgot your question.
Font size and or just number of things in the network.
Right. So
Can you repeat the question?
yeah. So the question was, how do you deal with the different kinds of votes from weak ties as well as strong ties, right? So in the system, let me get back to that slide. What we do is we have this model. We actually go and crawl your local social neighborhood, and we build this social network graph just for you of your friends and your friends of friends. And now we have basically this social bubble around you, right? And then we go and run essentially a social importance measure, network constraint, for example. So we actually calculate for each node that's in your local network how important that person would be to you. And then your votes, the vote of that URL is weighted by that score, right? That makes sense? And it turns out that network is actually really, really big. So for people, for example, that have, like for myself, for example, I think I followed 400 or 500 people. Those people, on average, and average is the wrong metric, but let's say 400 or 500 on top of that. So 500 times 500 is 250,000. So you're actually doing this modeling on top of 250,000 nodes for each person, right? Yeah.
What kind of database do you use for these two projects?
That's a very good question. As I mentioned in the Mr. Taggy work, we used MapReduce. So the database is a combination. In the crawling, we were using MySQL. So it gets crawled and dumped into MySQL. And then when the crawl comes to a certain phase, we dump all the crawl into MapReduce, which is the Hadoop file system. So we dump that into a Hadoop file system. And then that computes the index, the patterns and all that. And that's again, computed within the Hadoop framework. And then that index gets thrown over the firewall into a web server. So in that system, it's mostly MapReduce plus a MySQL engine. In the 0088 work, at least the talk that I just gave, this portion of the work, we actually built it all on top of let me think. Most of it was in Python and MySQL, but in the new Kai paper that I didn't have a chance to talk about today, which is about recommending conversations, that has all been rewritten. We took this entire system, rewrote it completely in MapReduce because it was not scaling up to the size that we needed. So for the most part, the database is all completely in MapReduce, in Hadoop. That's hard to measure. I didn't do a count recently, but let me tell you some numbers. So altogether, in our 60 machine cluster, we have about, if I remember correctly, about 48 terabytes worth of storage, where 48 is triple stored, triple replicated. So actually, altogether, we have probably close to over 200 terabytes worth of disk space. And inside of that Hadoop file system, we store all the delicious data, the index of that, plus the Twitter data, the index of that, and Wikipedia data, and some smattering of other things. So for the Twitter part, I think the last time I looked was on the order anywhere from 5 terabytes to 10 terabytes, something like that.
So we have time for more questions afterwards.
Yeah, I just have one.
You want to ask them afterwards?
Yeah.
The people have to go to class. So.
Oh, okay.
Thank you.
For more, please visit us at stanford.edu.